All right, we're moving on to the next speaker. I'm Victor Zhao, the president of the National Academy of Medicine. It's my great pleasure to introduce Amir Husain. Traversing an idea landscape, ideas generation, and pruning in synthetic systems. Side of intelligence, and we'll now turn our attention to the other side of the coin, artificial intelligence. Amir is the founder and CEO of Spark Cognition, an award-winning artificial intelligence company based in Austin, Texas. He's a prolific inventor, 22 US patents awarded, and over 40 pending applications. His work has published in leading tech journals, including Network World, Computer World, and many others. Now, he's also an author. His best-writing book, The Sentient Machine, Coming, Age of Artificial Intelligence, published just in 2017. So Amir has served as a founding member of the IBM Watson Board of Advisors and serves on the Board of Advisors for University of Texas at Austin Department of Medicine, pardon me, can't forget that, Department of Computer Science. An entrepreneur, inventor, and author, Amir has been recognized as Austin's top technology entrepreneur of the year and been awarded the Austin Under 40 Technology and Science Award. Amir, welcome. I turn it over to you.
I'd like to introduce the term traversing the ideascape and the idea of the ideascape. So when I was writing my book, The Sentient Machine, two of the questions that came up over and over were existential questions. They were, okay, either AI scientists will build AGI or they won't, but they might get pretty close. So if AI systems, either sufficiently advanced ANI systems across many different domains, specialist systems within specific domains, or a general intelligence is able to exhibit the level of capability that is parity or better than a human being, then what about us? And there's this sort of existential crisis. You're no longer good for muscle. If you're no longer good for mind, what are you good for? And fair enough. The other side of it is, as Professor Pinker also pointed out, the other part of this fear is, and by the way, they'll also kill us. So these are the two fears that I sort of addressed in my book, and I talked about what is of fundamental value. Why are we as human beings valuable in the age of artificial intelligence? Because the conventional wisdom would say, well, if they can outthink us and they can outwork us, then what could possibly be our value? And my conceptualization of this was to dream up of a universe of all possible ideas, all knowledge that is out there to be discovered in physical space. I closed my eyes and I saw this with all these gleaming, glowing objects, each representing an undiscovered idea. And in that space, whether we are human or AI, the purpose is to traverse that space. The purpose is to acquire knowledge. The purpose is to acquire experience. That space, by the way, is infinite. And in the closing pages of the book, and I'm kind of giving it away, but in the closing pages of the book, I talk about the fact that infinity is the great leveler of all speed. So the idea there being that whether or not we have a human being operating at a slow rate, or whether we have an artificial intelligence uncovering ideas at a very rapid rate, both of these creatures, both of these beings will uncover exactly the same percentage of the ideascape, which is 0%. And that, to me, was an interesting concept. So then what matters? If both of us, AI and human beings, are essentially going to uncover 0% of the ideascape, then what matters? What matters is perspective. Perspective in a specific sense of where you are instantiated within the ideascape. What parts of the ideascape you start your search from are actually what makes the difference, not the speed at which you search through the ideascape. And that really is a reference to the perspective. So that's the little background to why Ideascape and why I think about these problems in the sense of traversing the Ideascape. And today I'd like to sort of build on that concept a little bit more and talk about how I think about thinking. And the way I think about thinking is essentially this template, this frame of generating ideas and then pruning ideas, generating a large number of options and selecting from those options. So just by way of background really quickly, I run an AI company in Austin, but I'm also academically focused on AI, and I advise UT Austin. And also somewhat interestingly, I am part of the AI task force at CNAS, which is a fairly large think tank here in DC. And as part of this task force, one of the things that we're trying to do is now look at what the implications of the current level of technology to the domain of war, as an example, will be. With General John Allen, who's a four-star Marine Corps general, a couple of years ago, he and I wrote a piece called On Hyperwar, which is a conceptualization of what actually happens in the battlefield with ANI systems. And that has sort of become a field of study almost within the military. And you can see now the Chinese and the Russian reactions to all of that. So that's another aspect of the work that I'm focused on, trying to figure out how we manage that as a world, as a society, as a country. Okay. Now, coming back to the core message of the talk. So when we think about thinking, and I talked about idea generation and pruning. So again, coming up with a large number of things to consider, and then from this selecting some subset that is optimal for the time, optimal for the problem, optimal for the situation, pruning. Is there just one way to do this? And I think about this from the point of view of an engineer because I build these systems. So I think about this in the sense that in the late 50s, mid 50s, people like McCarthy employed logic to develop ideas and to drive ideas forward mechanistically. Then beyond that, we got artificial neural networks with work that was done by McCulloch and Pitts. And neural networks as a solver, as an approximator of a function, they became popular in that vein. And they could be used to generate ideas. And then also John Koza talked about genetic algorithms, and unlike the brain-inspired neural networks, John Koza was inspired by biology in general, and he said, well, here's another way to ideate. Another way to ideate is genetic algorithms. And then you had some folks achieve great success in these areas. For example, some discoveries were made by genetic algorithms in the space of VLSI that led to very efficient semiconductors that human beings hadn't designed. So these are at least three ways of generating ideas, and we know how to do them now. So again, an engineer's way of thinking about this, we know how to do this now. Okay. So the next step is, if you think about and if you read about the AI in the press, obviously deep learning, you can't avoid that. Deep learning is everywhere, and it's rightfully so. Why? Because deep learning has shown that almost all other traditional machine learning models can be outperformed given enough data with these deep networks. And wonderful, that's great. In this particular example, you see a large number of training images, and then you see an image with the question mark on it that this network is attempting to classify. Given a large number of cat images and a large number of dog images, there's nothing better than an artificial neural network, a deep network, to tell you whether the image you provided was a cat or a dog. Wonderful. Now, beyond this, though, there are also very simple ways to think. So going back to what I was talking about, idea generation and pruning. Let's look at a very simple example. This is a tree that identifies moves in a game of tic-tac-toe. And with no prior data, but only 3 rules, we're able to generate the state tree for tic-tac-toe because it has a very small space. So in this particular case, what does thinking mean in this micro context, in this sliver of the ideascape that we see in front of ourselves? Because each move represents an idea, and in this case, we've kind of dumbed down the concept of being able to generate these new ideas. So what is pruning in this context? Pruning in this context is looking forward to finding outcomes that are good, outcomes that are wins, and then working back to say, okay, given that I'm here and I can get to a win by traversing this path, this is perhaps the next move that I should make. Okay, so you have some sort of an evaluation and you decide to take that path. So this is a very simplistic form of search. Now, the problem is, of course, that most real-world challenges, even complex games, don't really fit well with this model where you can generate the entire space. So looking through the entire state space is a luxury that you don't get when you're dealing with anything particularly meaningful. But still, if you think about thinking and in this vein of generating ideas and then pruning them, there are in fact many ways to generate these ideas, and I'm using names of techniques across multiple decades of the development of artificial intelligence. So one way of generating ideas is the classic monkeys on typewriters. You've heard the old adage, given enough monkeys and typewriters, you could probably have war and peace, which is completely random. It'll take a lot of time. It's not the best way to do it, but yeah, it's possible. Okay. But what's somewhat better is applying some heuristic. For example, one heuristic might be don't let the monkeys type individual letters, only let them press keys that then type full words that make sense in English. So you could then constrain their effort and you could make it somewhat more efficient to get to something that makes sense. One simple heuristic. Or deep networks, right? Where we've trained deep networks on a large amount of data, and now there is a phenomenon of deep dreaming, where given training to these deep networks, we can ask them to say, you've seen a lot of faces, show me a face. And that face is not exactly a face that the network has seen. So in other words, it's a fake face, deep dreaming. So these are at least 3 examples, very simple, less simple, and even less simple, of ways in which you can generate an idea. And similarly, when you think about pruning these ideas, you can think about, again, an objective function. You can say, look, I know what state my game needs to be in order for me to win it. So based on that, I can look at an idea that's been generated, and I can evaluate it, and I can tell you whether it's good or bad. And at the same time, there might be certain domains where you can't do that, so you just have to unfurl possibilities, perhaps inside of a simulator. You have to try things and rank them. In some systems that we build, this is what we do, and I'll show you a few examples. Or again, with deep networks, where you can train these deep networks to become discriminators, to become entities that prune. So this basic ideate and prune design pattern is at the heart of what I suggest thinking can be. You generate possibilities and you prune possibilities based on experience. And even some very complex methods that these days are in fashion, for example, generative adversarial networks, deep networks, 2 of them, one working against each other, one trained to generate faces, the other one trained to look at those faces and discriminate between real human faces and fake faces. So 2 networks fighting against each other with the goal of making one learn how to spoof the other. Again, generation and pruning. All the way from tic-tac-toe to this, it's generation and pruning. Now, we've seen with this design pattern quite a lot of success in building real AI systems and solving problems that are real problems. So what are some of those real problems? One obvious one is that for a lot of real-world situations, there just isn't enough data. Deep learning is great, deep learning is wonderful, it needs too much data. We try and solve problems for airlines and aviation companies and the military and energy companies. And if we go back to them and say, could you please give me data on 1 million plane crashes? God forbid, right? There aren't 1 million plane crashes, thank God. And so the idea is, well, how do you learn from very small number of samples? The other problem is that when you train these networks, then you don't know what's going on. They are sort of opaque. There's this black box problem and the issue of explainability. And finally, which is a big one for me, is that the gosh darn things don't do anything on their own. There isn't any intrinsic motivation. And this intrinsic motivation, I don't just mean in the English sense of the word, I mean it in an artificial intelligence sense of the word. This is a term, actually, that came from Andrew Barto, and I'll touch on that here in a second. So again, needing too much data. In all these scenarios, we solve problems in all these scenarios. We build systems that take in sensor data, automatically build models, and predict when a turbine will fail. We take in sensor data and decide when to abort a takeoff on an aircraft. We take sensor data, we build models that predict all sorts of failures on rigs. And we cannot do them by requiring massive numbers of labeled data sets. They don't exist. So here is a short video that I'll show you. This is a real system that we've built. On the left, you see an autopilot, and this is the Boeing simulator. This was in partnership with Boeing. On the right, you see our autonomous pilot. Both of them now, the brake has been released, and both of them are hurtling down the runway. In a little bit, one of the engines will fail, and you'll see that written up on top. One of the engines will fail, and the autopilot is unable to really adapt to that kind of failure. So as the engine fails, the autopilot is now veering off the runway, and look at this aggressive maneuvering in comparison to the autopilot. This is the AI system, and this AI system is not only keeping everything on the runway, has now attained takeoff speed and has a safe takeoff. So this plane is now in the air, and this is the world's first autonomous RTO, takeoff rejection system built on AI. It was done, and it beats the best human pilots by 2 seconds on this decision, which means that as you're hurtling down at 120, 130 knots down the runway, 2 seconds is life and death. So this is an example of where we didn't have enough data. And so we built an AI to act as a generator running inside a simulator. And then by seeding that with a small number of human talented professionals like B-52 bombers, 747 pilots, 777 pilots, a small number of people, we were able to create a kernel of knowledge that automated takeoff AI was then able to replicate into thousands and thousands and thousands of takeoffs at every airport in the world, at every altitude, in every failure condition. So 3 problems, as I said. The second problem is connectionist systems are opaque. These networks, what are they learning? I mean, why do they act the way that they act? So there's a lot of problems that need to be solved here, but let me take you through very quickly one line of work that we're currently investing in, where we've had some success, and I don't know how successful this will be. So this might be a great success, or it might be a complete failure. These things can go either way. But I think it has some novelty, and it's an interesting idea. So the idea here is a brain surgeon looks at a human brain and can, through instruments, look at structural problems with the human brain and identify some sorts of malfunction. That's what brain surgeons do. Neurologists, that's what they do. In this particular case, what we have is a trained neural network and an untrained or a low-quality neural network. And both of them are essentially represented by this vector of numbers, right? So neural networks can be unfurled and can be represented as a big vector of numbers that capture their structure and capture their weights. The idea is to then apply huge numbers of well-to-do, badly configured networks, poor networks, structurally inefficient networks, and build a classifier that can try to find structural reasons why this network would exhibit problems. And the intuition here, the very simple base case, is if I gave you 2 networks, one of which had lots of different values, and one of which had just all ones across the entire vector, you don't need a classifier, you are the classifier. You can look at that and you can say, well, obviously, with all ones, the network isn't going to do anything. So the question is, these numbers are driving the interconnectivity of the neural pathways in the ANN. And to the extent that that is important to the performance of the ANN, then this discriminator can now be used to gauge the efficacy of ANNs. That's another area of work that we're investing in. And I know I have 2 minutes, so my last 2 slides. So the last point is one which actually I think about the most, this problem of intrinsic motivation. How do we get these things to do stuff on their own? And some people say that that's probably not a great idea. I think it's the best idea ever. And that is tied to sort of allowing these machines to build purpose, right? Because they have to be able to set for themselves some objective, some goal, and then pursue that goal. And then there are some philosophical questions associated with this, like, for example, is purpose emergent? And, you can read Albert Camus, and he tells you that there is no purpose, you find it yourself. There's existential nihilism, there's all sorts of schools of thought around this, but let the machines figure that out. I think giving them this capability is important as a path towards AGI. And my very last slide, imagine a child on day 0, and there's a very simplified model. So you have a hunger level, and you have one impulse, arguably two. You can cry and you can flail. And this is what you see as a child, a black and white, very pixelated field. So the idea here is that what moves together is one thing. The pixel, the light field that moves together is now identified as an object. That's one heuristic. The other thing that starts moving together, independent of the first thing, happens to be these pixels, which happens to be, in this case, a milk bottle. And it so happens that the milk bottle, being present for a while, causes a reduction in that impulse, in that hunger level impulse. That hunger level impulse is going down. Now, the 0-day child, as a Bayesian reasoner, starts to put 2 and 2 together. What he discovers is that if mother, then milk bottle, because the co-occurrence of these two objects is very high. So mother, likely milk bottle, and crying, likely mother. So there's only two things they can do, flail and cry. If they only flail and the mother is in the next room, that's a failed attempt to placate hunger, right? They keep doing that, they're not going to be a successful baby. So they got to cry, and then that calls the mother, and the mother also has built up a model which says if he's crying, it's either the diaper or the food. And so you bring the milk bottle, and there you go, and that is a reinforced behavior. So the idea here is, what is the minimum set of such fundamental kernel heuristics that you can put into a system and allow it to develop libraries of independent objects and then reason over those objects in order to construct a model of the world. And that's it. I'll end here. Thank you very much. Yeah, absolutely. Yes, my pleasure. Questions, yes.
Hi there. So it sounds like, just from your end there, you were saying that you were enthusiastic about AGI. Is that what I heard? You were sort of enthusiastic about software essentially having volition and agency?
Yeah.
So let's assume that that's possible, that software can be written that has volition and agency. Once we assume it's possible to write such software, we could assume that that volition could be escalated over time. The level of volition and agency could have a positive curve over time. Would that be a fair assumption?
Perhaps.
Okay, so then the question is, if there were malicious forces that were designing those, since you had spoken about defense issues, if there were malicious forces intentionally designing malicious actions into that agency, that would be a reasonable fear, because a malicious actor would certainly design malicious software. And if those malicious forces had no care, let's just leave out military for a second and leave out state actors. If those malicious forces were hackers, we could imagine fairly sophisticated hackers designing malicious software that had agency. Am I missing something in that curve, or would that be something to be concerned about?
Well, I wouldn't say that you shouldn't be concerned about it. I'm perpetually concerned about almost everything. I'm a paranoid individual. But I have to say two specific things in context of that. One of which is that it's not clear to me that this race towards this kind of AGI that we talk about is the only means of introducing malevolence to the world. If you hear detractors of artificial intelligence and AGI in particular talk about the great menace, I think, what is it, the demon of AGI, it would appear as if for the first time Pandora's box is about to be opened and the woes of the world are about to be unleashed on humanity. But I don't know, in my experience and in my reading of history, all the malice that I have read about, seen, witnessed, or sadly been subjected to, has all come from the mind of man. So as far as my Bayesian priors are concerned, I am highly biased towards the malevolence of man. Now, your other part of this question is, and by the way, I have never seen machines being malicious. The other part of this is, okay, but what about a man building a machine that is malicious? Well, they do that all the time. And those machines don't need to be smart. In fact, Genghis Khan with the US or Russian nuclear capability would be the end of the world. We have produced our humanity. Professor Pinker in his book talks about appealing to higher causes and the finer slivers of niceness that we have inside us. But we have a lot of the human condition still to overcome. At this point, if you were to ask me, do I trust the proved maliciousness of man more, or do I fear the unseen maliciousness of a machine that does not exist? I would have to say I worry about the former a lot more.
Just a quick observation of two analogies when you were describing the sort of exponential combinatorial. What was the term you used? The before the pruning was
Ideation?
Ideation and pruning.
Yeah.
I think the basis of neural growth from the time that an infant is born until about age 3 or 4, you have that sort of exponential increase in the number of synaptic connections and then the sort of precipitous pruning. And the same thing, analogously, in my world of venture capital, happens when new entrants come into an industry. And you have an exponential increase in the number of entrants and then a precipitous pruning, and then there are 3 or 4 players left.
Actually, that's a very, very interesting observation. One of my core areas of fascination is natural computation in natural systems and also social systems. Just like an ant colony computes to the point where ant colony optimization is now an algorithm in computer science. It can be formalized to that degree. Social systems amongst humans also are performing computation all the time. I was sharing with Professor Porter one tremendously beautiful example of an analog computer. So think about 4 or 5 glass tubes vertically set, all connected with a pipe that ties them all together. But there is a valve disconnecting each one of the vertical pipes from each other, right? And initially all the valves are closed. These bottles are marked with a number. So you put water at level 4, level 3, level 2, level 1, level 8, and then you suddenly open all the valves. In constant time, the average of all the numbers is computed by gravity immediately. And if you think about that as a general purpose computer, it's something that takes a lot of time. So what you alluded to, which is these examples of nature, we don't know much. We don't know much yet. There's a lot to still look for. There's a lot of better computing paradigms to look for. I think there is a lot of grace and beauty to be found just in the way nature computes.
Hi, I'm wondering how you're going to define or understand true agency in a machine, because I understand that right now machines only do what we program them to do, but you could argue that humans only do what we're programmed to do. It sort of seems like it's tied into what we were talking about earlier with this question of consciousness. If we don't fully understand it in ourselves, then how are we going to recognize it when we see it in AI?
One quick check would be, it would probably be necessary but not sufficient, but it would be a good indication, is if you had a varied change in the objective function that an AI was doing on its own. In other words, it was setting its own goals. Because if you go back to the definition of intelligence, one of the things that we say, and there seems to be broad agreement on this definition, is that the more intelligent something is, the grander the goal setting that entity can then engage in. And if you think about the objective function as a goal, and that objective function is now via intrinsic motivation, not extrinsic factors alone, via intrinsic motivation is changing, maybe frequently or to something that requires a lot more work to be achieved and in some sense is more grand, then I think that would be one indicator.